Okay, first of all, thank you, organizers, for such a tricky experience for me to first time make such talk. I try to explain what our recent result, which is still not, most of them are not published. It's about Chimera switching in couplet oscillators with inertia. And our model is promoter model with inertia. Let's see if I can now pointer. Actually, if we remove a second derivative, we have standard promoter switch model, which well studied also for Chimera states. And that model with second derivative is actually inertia is Newton law. So it's much closer to real system. In particular, it can be model pendular dynamics and others. Okay, what we consider now, we consider model with global coupling, where we plan to show Chimera states, actually weak Chimera states, for small networks with n equals 3, 4, and 5 oscillators, globally coupled. The parameters m mass will be put to 0, damping to 1, damping to 0, 1. And then we have two parameters. Alpha is phase shift, and the mu is coupling strength. And we will play in this parameter plane and study what can be there. This is my joint work with group from TU Lodz, from Patricia Yaras, from a member of our group, Roman Levchenko, Sergei Brzezinski, a PhD student, and Tomasz Kapitani. Okay, so here we give examples what is going on in such system. For n equals 3, 4, and 5, these are typical example for the behavior of trajectories for Chimera states and for basins which can be found there. And as we see, that switching of Chimera switching arises beginning from n equals 3, also for n equals 4, and it becomes absolutely complicated for n equals 5. Here is a color bar indicate Chimera different types. You see, depending 0 and 1, it means that 0 means this main frequency for synchronous motions, and 1 means that we have a phase which rotate with different average. Then I will start with n equals 3, which is just a few slides reference to the paper 3 years ago. And what we found there, we found two types of chimeras. In-phase chimera states, two oscillators are identically equal, one rotate with different frequency, and antiphase chimera with when two is antiphase and one is rotate with different frequency. This is here are region of such chimera states, so they are very much typical for this system. Actually, here is maximal Lyapunov exponents for the line here, where we can see the situation when chimera becomes chaotic chimera. And then for this chaotic chimera, we observed the time, the behavior like this. Look, this is chaotic chimera states at the interval 100,000 time units. Two oscillators rotate slowly, and one rotate faster. And this is the same shown at the time interval 10,000 and the same the interval 1,000. So we see that we see chaotic behavior and all these chimera states. And then what is going on with increased parameter alpha? Just shown here. You see that first we have appearance of heteroclinic switching. You see, actually, this is interval 50,000 time units. So CSS switching is a very long period, and it becomes more and more often, and this is already starts this behavior beginning from n equal 3. However, it takes in quite small parameter regions, which is there shown between these two Chimera states. Then let's go to n equal 4. N equal 4 is popular network. Is considered by many people, but mostly in the case when we have two groups, 2 plus 2. Our situation is completely symmetric. There's 4 globally symmetrically coupled elements, and chimeras rise naturally in such system. So this is and this is a parameter region for situation what is going there. Yellow region, this is a region for in-phase Chimera states. So 3 oscillators are in phase, identically in phase, and one rotate faster. Then blue region is a region for anti-phase chimeras. You see that those two rotating faster are in anti-phase, and then there is so-called rotating wave chimera. One is still the main synchronous frequency, but 3 other rotate in rotating waves. This region shown here. And a very important things here is so-called riddling shadow. So if you are in the parameter region, you can observe chimera forever, they are stable. But as soon as you come to the region here, you have some transiental chimeras. Also was mentioned in previous talk that we have behavior which can end in any unpredictable moment of time, but it's still in this shadow show. Here is more probable, here is less probable, but this dynamics is essential part of the system. What is also interesting is a singular point A here with pi/2, where all Chimera regions start in form of Arnold tanks. So if we go through this region, we can get, I don't know, sorry, yeah. So moving through the region, we have first Chimera with 1 splitted element, then there will be this 2, and then 3, and finally we have classical rotating wave, which is well known like splash state, but rotating. Okay, and what is interesting here, maybe I will show. What is interesting is Chimera with 3 elements which are rotating fast. You see, this is type 110. 0, it corresponds to frequency of synchronous state, and 3 rotate faster. As you see, they are here. We spent some time trying to understand this behavior. And okay, maybe I will show. This behavior exists in very thin orange tank here, which goes to pi/2. And we make simulation up to 100 million time units, try to get stability of this state. Finally, we could not do it. Here this parameter value quite close to pi/2. We still have switching, which can be after tens million iterations, but finally we have chaotic Chimera which switch all the time. So we concluded that this is chaotic switching Chimera only. What is else interesting for n equal 4 case? they're always present in phase lock state. Okay, so you know that for I from 0 to pi over 2, there is always synchronous state exists, which rotate with some with velocity depending on alpha. And then in the region for in the region for beginning from pi over 2 to the right, there is always so-called antipodal state, or Eckhart called it the double antipodal state, which means states like this plotted here. You see there are two pair of antiphase oscillators, and they with some angle between them. And this is a fixed state of the system. Actually, if you put to 0 right hand of this equation, they just give 0 here. And finally, we are getting it's completely stocked situation in our system. And this is because of even number of n, and for n equal 4, it's always present. So antipodal states can be written here. They exist for any angle b, but stability depends on b. And the region of stability is here shown as dashed line depending on b. And so we can conclude that there is a one-dimensional manifold of antipodal states. They are stable and coexist with chimeras at any alpha larger than pi over 2. So it makes dynamics of the system very much unpredictable. If we have some kind of behavior, it always coexists with one-dimensional manifold of such state. And okay, I see this is my first talk. And then the behavior, the switching behavior can stop anytime, and you will be attracted to one of the antipodal state like this. And then I would use such term as individual variability. Actually, there is a parameter beta, and you can be attracted to any of them. Okay, so let me come to n equal 5 case, which is already for odd number, and then there is no antipodal states. Again, we have 5 oscillators, globally coupled, the parameters like this. And I do not show the full parameter verification diagram. It's quite complicated and not finished yet. But what we done, we just show examples of dynamics fixing m equal 0, 1, and moving along this parameter line here and show what is going on there. What is difference n equal 5 problem is that there is a full open region of chaotic chimera states. Look, so this is, it's quite big, quite wide region where dynamics is like here. So you see this is phase and this is velocity. And then there are 3 equal oscillators, identically equal, and 2 others are rotate chaotically. Actually, the system can be reduced to the Chimera manifold, which will be 3-dimensional or 6-dimensional if you wish. And then the behavior is the classical behavior when you have attractor, chaotic attractor in the manifold, and then we study its stability, loss stability with change in parameters. Look what is going on if we, okay, if we go to the right along this line. So first we have chaotic chimera states and our simulation here up to 20 million. Yeah. And so nothing happened. We inside the chaotic chimera region. And then, and this is in the point you see 6350. Then just moving just one step in 10,000, we already got EC1 to switching at the interval of 20 million time units. You see very small increase in alpha to the right gives you more and more switching, switching here, and quite fast. You see at 20 million iterations, the behavior looks like a mess. But now we make the following trick. We consider let's come from 20 million to 200,000. And you see, if you take very small piece here and then increase scale by 100, then we see that this kind of behavior, switching behavior still continues, but it's already at a different scale. And then we continue increase alpha, and we see that again it becomes more and more recurrent. And finally, we make the same trick. We comes now to on 10,000 scale, and we still see this the chaotic two chimeras, and finally at 1,000 scale looks like here. What we have can see here. Okay, maybe here. Look, this is one chimera. It's in phase chimera. This is in our terminology, it's in phase chimera. And this is antiphase chimera. You see those split elements are in antiphase. What is here? Look, this is actually three elements split it, and then they again piece of one, then again piece of two, piece of three, and one. Actually, the system comes to the behavior when we have switching between 1, 2, and 3 chimeras switching. And what is important, such type of behavior happen in wide parameter region, and nothing other can be observed there. So this is, I show example. This is my example how with further increase, you see we will increase alpha even more. And here's typical example at the 1,000 time interval. Look here, this is one chimera, this is two chimera, then again 1, 2, then this is 3, then 1. This is again moving further. We are getting the same time behavior, and for wide parameter region. And I will say that this is I would say maybe a novel type of behavior that exists in whole parameter region, and nothing different can be observed there. And the question, what is the end of such story? For this, let me come to bifurcation diagram here. So we moved along this line, and what is here, this region which is shown here in gray, this is a region of switching, chimera switching behavior, which is quite wide. And finally, we come to so-called antipodal chimera states, which means that these two pairs are in antiphase, those which are there. And look how it's happened, like this. So here you see quite complicated behavior, and finally it just dropped to this type antipodal chimera state, which is also shown here. You see this is only one oscillator is left rotating with original synchronous frequency, and there are two pair in antiphase. And maybe coming to the last my slide. Interesting question is about average switching period when we come to the bifurcation. First of all, how switching arises? What is the mechanism of this? So what we found, chimera switching arises in the riddling bifurcation. This is standard problem from chaotic synchronization. You have chaotic, which I was involved in that some 20 years ago. So there is a manifold, this invariant manifold, where you have a chaotic attractor, and then the question how this chaotic attractor can lose its stability. A question was solved there that it loses stability normally in riddling bifurcation, which means that inside the attractor there arise low periodic orbit, which becomes transversally unstable. The whole attractor is still stable. Transverse Lyapunov exponents are still negative, but there is a path for trajectory just to leave this attractor. This is riddling bifurcation, which was determined by in Maryland group of York in beginning of 90s, and then here what we and the question. And then the next bifurcation will be blowout bifurcation. It's shown here. Then transverse Lyapunov exponents already becomes positive. So here is what we found in logarithmic scale for average period switching. Actually, our experiment was only six trail for each parameter value, and then you see in logarithm scale, it looks like super exponential, even super exponential. Yeah, this is riddling bifurcation point, and what I shown, pictures I shown, there was pictures like moving along this line. So you see that the average period decreases even super exponentially. So we just may take one more logarithm to show that the law is like exponent from difference in parameter, but there is some positive parameter gamma could be which gives this line straight line. And it's interesting was for us to find that you see this point. In this point, you see that asymptotic changes. This is point of blowout bifurcation. So in this moment, two transverse Lyapunov exponents becomes positive, and it's changed asymptotic of switching. So switching law changes after the blowout bifurcation. So my conclusion, I come to conclusion. We have not much time, so I would say that we can speak about Chimera complexity, which includes a huge multistability of the states. And I show an example of basins, and basins are riddling, basins are intermediate, and it was also shown in this talk today. Yeah, that its basins could be very much complicated, and number of attractors could be also huge. And this is only for small systems, for small network, but for larger network, of course, it becomes a terribly complicated picture. And then basins is riddling. It's typically observed in many our examples. And the last complicated is heteroclinic switching. Heteroclinic switching, which means that there is a full wide regions where the behavior represents heteroclinic switching between chimeras of different type chimeras with different number of elements which are splitted from the main synchronized clusters. And this is one peculiarity. And the second peculiarity is that presence of so-called antipodal points, which are present for even number network with even number, and then which means that such switching can be transiental, and it can continue very long or can just stop and drop to an antipodal. So this is a reality of Chimera systems, and I think it would be good to study more this phenomenon. Okay. So thank you. Thank you.
Thank you. Thank you, Yuriy. And thank you for your talk. We have one question by Rico Berner. For n equals 4, you have shown the stability results for the antiphase state. can this result be extended to any even n?
Yeah, I would be happy to know this. Yeah. So
You would?
It can be extended for any even n.
Yeah.
But well, it's not shown yet.
Mm-hmm. Well, this is a similar question which I had. Of course, symmetry of the network plays a major role in your work, and so you have shown or classified the cases n equals 3, n equals 4, n equals 5. What conclusions can you generally deduce on larger networks from these results on 3, 4, 5? Is there a simple rule like even, as in the question by Rico, or could you say that some networks, for example, 6 would display similar behavior as n equals 3?
Yeah.
Or is it more complex?
Yes, more complex. I can come to the riddling shadow. So for n equals 4, we have a region of Chimera states, and we have called riddling shadow, where where we have coating switching dynamics, which is transiental, and the can be very long. This is a typical situation for even, but for n5, it's a real region. It's a real region. You see, this is this gray region. All this region, nothing except of is there, and it's never stopped. It's not transiental. It's real Chimera switching between different type Chimera, between those which are to the left, those which are to the right, but then they have pieces of this. So this is different between even and odd is different. And of course, increasing n, I think it will be only more complicated.
Okay, thank you. There is one question by Sergei Yanchuk. How do you detect the riddling bifurcation?
Okay, thank you for this question. Unfortunately, I had no time. So we found actually a responsible state for the riddling bifurcation. Look for instance here, example of behavior. You see there is static behaviors, and finally it becomes yellow. What does it mean? It means that the behavior spent some time close to low periodic, for some low periodic solution, which is transversally unstable, and then it makes switch. So switching in many cases, it's right. So we actually found this low periodic orbit, but but the work is in the process. I really have to study more.